We'll start this section by solving what are called polynomial inequalities. Usually we're solving equations with equal signs, but when we're solving inequalities, we'll see, less than or greater than or equal to or any of those inequality symbols in there. And one important difference between solving an inequality versus solving an equation is if we solve an equation, we can get, maybe one x value like x equals 5 or multiple like x equals 2, x equals 5. An inequality solution, the solution to a polynomial inequality will be the set of all values that make the inequality a true statement. So it's going to be an interval of solutions. So instead of x equals 2, we could get the solution interval from 2 to 5. So any value in that range could be a solution. All right, so we'll start off with question number 1, where it says to solve x squared plus x minus 12 is less than or equal to 0. And over here on the right, I sketched out some quick instructions for the steps that we're about to follow. So first it says I need to find my boundary values, what I'm calling boundary values. And to do this, you will set up your expression on the left, I'm calling it f of x, set it equal to 0, solve for x, and that will give you your boundary values to set up your intervals in your sign chart. So I go through the steps over here, but we're taking x squared plus x minus 12, and we're factoring that and setting it equal to 0. X squared plus x minus 12 equals 0. Oops, sorry. X squared plus, there we go. Then we factor to get x plus 4 times x minus 3 equals 0. And we get x equals negative 4, x equals positive 3 as our boundary values. Okay, so how do I use negative 4 and positive 3? Going down here, this is what I call our sign chart. So across the bottom on that axis, you have a number line. And remember that we got negative 4 and positive 3. So at negative 4 and at positive 3, you just create, usually I used a vertical dashed line here, but you just create a little boundary, a visual boundary, which creates 3 different intervals. An interval over here to the left of negative 4, interval between negative 4 and 3, and an interval to the right of positive 3. So you use your boundary values to separate out your intervals along your number line. So that's step 1. Okay, step 2, pick a test point in each interval. So we have 1, 2, 3 intervals, so we'll have 1, 2, 3 test points. So pick a test point in each interval and evaluate in your expression, I'm calling that f of x, at each one of your test points to establish a sign for each interval. Okay, so we can pick any value in these intervals. So for this far left interval, I could pick negative 10 million if I wanted to. It'd be kind of weird, but I could do it. But why don't I just pick a negative 7 instead? So any value in that interval to the left of negative 4 is fine. Don't pick the boundary values themselves, but anything in between boundary values or to the left or to the right is fine. So let's say our first test point is x equals negative 7. All right, so remember when we factored our expression over on the left, we factored it as x plus 4 times x minus 3. We could use the original function x squared plus x minus 12, but I usually find that it's easier to work with the factored form. So I'm going to work with the factors. So I'm going to take those factors, x plus 4 times x minus 3, and I'm going to replace x with my test point, negative 7 plus 4 and negative 7 minus 3. So negative 7 plus 4 gives me negative 3. Negative 7 minus 3 gives me negative 10. Negative 3 times negative 10 multiplies to 30. But all I care about is it's a positive 30. So I'm going to label that interval with a positive sign. All right, so what this tells me is if I picked any value in that interval, I should come up with a positive result. It won't be positive 30, but it should be positive. So let me just double check that. So maybe I'll pick negative 8 as a second test point, okay? So I'd have negative 8 plus 4 times negative 8 minus 3. So this would be negative 4 times negative 11, which gives me positive 44. So any value in that interval should produce a positive value when you plug it into those factors, okay? So I'll go ahead and get rid of the negative 8. That was just a test of my test point. All right, so if I pick any value, so it doesn't matter if you had picked negative 5, we still would have gotten a positive number. The key is to establish the sign. And I also want to point out, in that first example, I plugged in negative 7 and I calculated the exact numbers, and that's great. If you want to do that, that's totally fine. But all I care about is this sign, okay? So going forward, I'm going to start off negative 7 plus 4 times negative 7 minus 3. And then I'm just going to say, well, negative 7 plus 4 is going to be some negative number. Negative 7 minus 3 is going to be some negative number. And I know a negative times a negative multiplies to a positive. So I don't even care about the numbers themselves. I just care about the signs, hence the name sign chart. Okay. All right, so in the middle here, I like to pick 0. Usually 0 is a pretty easy test point when I can get away with choosing it. So plugging it into my factors, I would have 0 plus 4 times 0 minus 3. 0 plus 4 is positive. Positive 4, but I just care about the positive. 0 minus 3 is negative. Negative 3, but I just care about the negative. And I know that some positive number times some negative number equals a negative overall. So I can label that middle section, that middle interval, with a negative. And choosing my final test point, doesn't matter what I pick, so maybe I'll just pick positive 8 here. Plugging those into my factors, 8 plus 4 times 8 minus 3 would be positive times positive, which gives me an overall positive result. Okay. So I found a test point in each interval, right? I found 3 different test points, negative 7, 0, and 8. I plugged them into the factored form, and I calculated not necessarily a number, but a sign for each test point, and I can apply that to the entire interval in general. Okay, so I set up my intervals using my boundary values. I found my test points. I set up my signs. And by the way, this won't always happen. It's certainly possible that it doesn't, but very often you'll see this alternating pattern, plus, minus, plus. So when you see that, that's the most typical pattern. You could see a plus, minus, minus, or a minus, minus, plus, or something like that. But if you do, just double check, because oftentimes you've just made a little typo somewhere. It's not impossible to get that, but it's much more common to get this alternating pattern. So just a little tip. Okay, so now we did all that work. What on earth are we looking at? We want to write the solution in interval notation. So now I'm going to go all the way back to my original question. So this said, solve x squared plus x minus 12 is less than or equal to 0. So if something is less than or equal to 0, numbers that are less than 0 are negative. Negative. Right? So we want negative values or equal to 0. Okay? But less than 0 means it's negative. Less than or equal to 0 means it's negative or exactly equal to 0. So how does that help us? Well, we made this sign chart. So I'm going to pick out the areas of my sign chart where I have negative values, right? So that occurs inside this interval, where my values are negative. I'm not going to include either of the positive signs on the left and the right-hand side. And I sketched this out kind of messily using my highlighter here. I sketched this out using square brackets because it's less than or equal to, right? Less than or equal to, I'm going to use square brackets to contain my interval. If it had been strictly less than, then I wouldn't want to equal these boundary values. But because it's okay that my function equals 0, I can include -4 and +3. Okay, remember that we found -4 and +3 because they make our function equal to 0. So we can include -4 and we can include +3 in our solution set. So the solution in interval notation is any value from -4 up to +3, including those endpoints. Okay, so your rule down here, if the inequality symbol contains greater than or equal to or greater than, you want the positive parts of the chart. If your inequality contains less than or equal to, you want the negative parts of the chart, and that's the rule that we just followed, right? And if you have less than or equal to or greater than or equal to, you use your square brackets. If you have less than or greater than, you're going to use your rounded parentheses and not include those end values. Okay. Now, we're looking at the same expression, x squared plus x minus 12. That's the same thing we did in number 1. But now all we're doing is changing the inequality, right, to less than 0, to greater than or equal to 0, and to greater than 0. So remember our sign chart from before. We found our boundary values, -4 and +3. We used our test points. We got positive, negative, positive, that alternating pattern in our sign chart. So let's write out our solutions in interval notation. So for number 2, x squared plus x minus 12 is less than 0. So now for number 2, I'm again looking for the negative sign on my sign chart, but I'm going to use rounded parentheses because it's strictly less than. So I'm going to go rounded parenthesis, -4, up to 3 rounded parenthesis. For number 3, x squared plus x minus 12 is greater than or equal to 0. Greater than or equal to 0. Now I want positive or equal to 0, so I can use those square brackets since it's okay if my solutions equal 0. Or create, a function that's equal to 0. Okay, so now I'm using the positive intervals, so that would be from -infinity up to -4, square bracket, and from +3, square bracket, up to +infinity. Connect with a union symbol. Remember that at negative and positive infinity, I always use rounded parentheses no matter what, and then square brackets at those boundary values, -4 and 3. All right, and then finally, for number 4, x squared plus x minus 12 is greater than 0. Again, I'm looking for my positive intervals, but because it's strictly greater than 0, now I'm using rounded parentheses. So now I'm going from -infinity up to -4 rounded parenthesis, and then rounded parenthesis 3 to +infinity. All right, so they all have those boundary values in the answers. It's just whether we're looking for the negative portion or positive portion of the sign chart based entirely on that inequality, and whether we're including or excluding those endpoints. All right, and again, looking at x squared plus x minus 12, up here we have x squared plus x minus 12 equals 0. So we have an equation, and this would be solved by the zeros of this function, x equals -4 or x equals +3. Visually, these are the x-intercepts of this function, right? So that's for an equation. Now, if you look at x squared plus x minus 12 is less than or equal to 0. Less than or equal to 0 represents our negative numbers, right? So now we're going below our x-axis. Because it's less than or equal to 0, we are including those endpoints of -4 and +3. So remember my solution was from -4 to +3. this contains all of the solutions to that inequality. X squared plus x minus 12 is strictly less than 0. So again, we're in negative territory. We're looking at negative values below our axis. But now we have open circles, right? Open circles at -4 and at +3. Because we can't equal -4 and we can't equal +3 because that would give us exactly 0, we want to be strictly less than 0. We want to be strictly less than 0. And then in our last two cases, x squared plus x minus 12 is greater than or equal to 0. So now we want to be above our x-axis in positive territory, right? So we want to be above our horizontal x-axis. And the x values that allow us to do that are from -∞ to -4 or 3 to +∞. And because it's greater than or equal to, we're including those boundary values. Over here, x squared plus x minus 12 is strictly greater than 0. So again, we have that positive portion above our x-axis where our function value is positive, but we're using open circles at -4, open circle at +3, corresponding to rounded parentheses at -4 and +3.